Reverberation is nothing but the persistence of sound even after the source is stopped. Density is also the constant one, whichever I had given earlier for Newton's formula. And now let us consider a rho. Rho is the density. You know the difference between progressive wave and standing wave. Progressive wave are the wave which keeps on moving, correct? So the standing wave is the one which doesn't move. Hello everyone, I'm Brinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to Chapter 15, Session 3. And the chapter name is Waves. So in today's class, let us study regarding the Newton's formula for speed of sound in air, as well as the LAPLACE correction which was given to Newton's law, types of reflection of waves, that is echo, reverberations, and what is a standing wave and how does the standing wave acts when it is sent through a hollow pipe, that is an open pipe or a closed pipe. So here waves, under waves, we study regarding the sound waves. So what is that sound waves? Sound waves are the longitudinal waves. So here we check the speed of a longitudinal waves in gas. Therefore, Newton considered isothermal process, which is said that by considering the ideal gas, we have got ideal gas equation to be PV is equal to nRT. And since Newton considered an isothermal process, so here this process is a process where the temperature is said to be constant. So here we have got what is constant? Temperature constant. So here the equation is given as PV is equal to constant, because where the temperature is constant, we have got our term as P into V by Boyle's law. So here Newton considers isothermal process, that is PV is equal to constant. Now let us differentiate this equation, that is equation 1, with the help of the volume. So we have, on differentiating, this concept, we will have d of PV divided by dV, so which is equal to constant. By using product rule of differentiation, we have P into dV by dV plus, again you have to differentiate dP keeping V constant, so dP by dV, which is equal to 0. So what remains is P plus V into dP by dV. Now to cancel dV, I will have to multiply the whole term by, that is the whole equation by dV. So we have on multiplying with dV, the equation, that is the above equation, becomes P into dV plus V into dP, because dV and dV gets cancelled. So we have, which is equal to 0. Let me retain P as it is and get all the other terms towards the other side. P divided by dV. So this is in the form of the equation of a bulk modulus, that is B, because bulk modulus can be given as B is equal to dP divided by dV divided by V. So this is all about the bulk modulus equation. So what is the equation at final? So it is P is equal to B. So bulk modulus will be equal to the pressure which is exerted. So now here, having P is equal to B, we have got the speed. In order to calculate the speed of a longitudinal wave, generally we have an equation which is given as the speed, that is velocity, is equal to root of bulk modulus to the density. So here we have, instead of B, we replace the B by P divided by rho. Why? Because since B is equal to P, I just interchange. So having this formula, this is said to be the speed of sound in air, which was given by Newton. So having the standard temperature pressure for air, the pressure is said to be 1.013 into 10 raised to 5 pascals, and rho is said to be 1.293 kg per meter cube. So this will be the pressure as well as the density of air at standard temperature pressure. So on solving these two equations by applying it to V, I have got the velocity as 280 meter per second. So I have got the velocity 280 meter per second, wherein experimentally calculated value will be 332. So experimentally calculated value of V is 332 meter per second. So it is very far, it is not even approximate to the experimental value, because of which LAPLACE gave certain corrections. That correction was given as, now LAPLACE correction, that is Newton considered temperature to be the constant. But in case of the longitudinal wave, when it undergoes compressions as well as rarefaction, compression and rarefactions, that is, the compression part, the temperature is said to be high. At the rarefied part, the temperature is said to be low. So there is variation of temperature because the maintenance of constant temperature is not possible in certain interval of time. Okay, so that is why this temperature is not said to be constant, because of which LAPLACE considered adiabatic process. Adiabatic process. So what was there in this adiabatic process? They consider an equation to be PV gamma is equal to a constant. So this gamma representation is nothing but it is the ratio of two specific heat capacity. So we have got PV gamma is constant. So let us differentiate this, that is the equation 1, differentiating equation 1 with respect to dV. So equation 1 becomes d of PV gamma and you have got dV which is equal to 0. So retain P as it is, dV gamma divided by dV plus V gamma dP by dV is equal to 0. So we have this equation as P into dV gamma divided by dV. This is of the equation V to the power of n. So if you consider this as V to the power of n, what do you get? N into V n minus 1. So this is the concept over here. So the same concept is applied, that is the formula of differentiation, x to the power of n formula. So gamma V gamma minus 1 plus we have V gamma dP by dV is equal to 0. So when this is a case, I'll have to first of all discard dV. So when that is the case, I will multiply throughout by dV. So I have got V gamma minus 1 into dV plus V gamma into dP is equal to 0. Now I want to discard my V gamma minus 1. In order to discard this position, I have to divide it by the same term so that I can cancel out. So divide the above equation completely by V gamma minus 1. So I have got P gamma into dV plus V gamma divided by V gamma minus 1 into dP. So this can be written as like P gamma into V dV plus V gamma divided by V gamma minus 1. When this term goes up, it becomes plus gamma minus gamma plus 1. So plus gamma minus gamma cancels. So you have got V into dp. It will be v to the power of 1. That is why I am taking only v into dp is equal to 0. So this equation is now present, that is p gamma into dv plus v into dp is equal to 0. So the equation was p gamma into dv plus v gamma into dp is equal to 0. So retain only p gamma with you, take everything the other side, so it becomes minus v gamma into dp divided by dv. So this is the same as that of the bulk modulus, so you get p gamma is equal to b. So this will be the equation. So according to the speed of the longitudinal waves, we have got the general equation said to be v is the velocity which is equal to root of the bulk modulus to the density. So when this is the case, when you are applying equation 2 to this equation, you get it as v is equal to root of what is b? B is nothing but p gamma or gamma p into gamma divided by rho. So here this equation represents the Laplace correction. This equation is said to be Laplace correction. That is, just you add up gamma to the previous equation which was given by Newton, wherein your pressure is the standard temperature pressure of air, as well as density is also the constant one whichever I had given earlier for Newton's formula. And now let us consider a rho. Rho is the density. And now let us consider gamma. Gamma, it's the ratio of two specific heats, that is gamma is equal to ratio of two specific heats, that is specific heat at constant pressure, specific heat at constant volume. So when this is a case, its specific heat is said to be 7/5, and applying those value here, you will get the answer for the velocity of sound and gas as 331.2 meter per second, which is said to be the velocity, which is approximately equal to the experimentally calculated velocity, that is 332 meter per second. So that's all about the Laplace correction, wherein the formula which was given by Laplace were most valid because it obeyed the experimental value. It synced with the experimental value. So that's all about your Newton's formula for speed of longitudinal waves, as well as the correction which was given to the Newton's law. Now let us move to principle of superposition. So what is the superposition of the waves? It is nothing but intersection of two waves. So both the waves are mixed with each other. That is all about superposing of one wave with the other wave. So what does it say? When a medium is disturbed, that means medium is undergoing disturbance, in the sense there is a creation of wave over there. So in a science term, what do we say? The disturbance of a medium means there is a presence of wave. So when a medium is disturbed simultaneously by any number of waves, so any number of waves, it can be more than two waves also. So here, when the medium is disturbed simultaneously by any number of waves, the displacement of medium at every point. So displacement of the medium at every point, at every instant is the resultant. So it is summing up of the disturbance which is created in the medium by the particles. So this is all about the superposition. Both the waves are superimposing on each other. So that is all about your superposition of waves. So superposition, in a simple manner, we can say that intermixing of two waves in order to get a new wave, wherein the superposition of waves are valid only for the large displacement in mechanical waves, and it doesn't hold good for the larger displacement of the particles in a medium. So that's all about your superposition of waves. Now let us move to reflection of waves. So I hope you all have seen the reflection of waves, that is, you have heard the reflection of waves. That is all about the longitudinal waves reflecting back, that is sound waves reflecting back. Whenever you produce a sound, what happens to the waves? How is the wave moving and reaching the other end? That is due to the medium which is present between the source and the receiver. So when there is a medium between source and receiver, whatever you talk or the voice which is audible, it comes and reaches the observer. That is all due to the air, and it is the medium which has certain particles. Particles are necessary for the transfer of energy and we can hear the sound. So if suppose at the observer's end, if there is a rigid wall or a rigid object, what happens to the audio given from the source? The audio which travels through the medium, it hits the rigid surface and it gets back. That is the pitching. You have studied in light also. That is, if you just pass the light to an object which is silverized one side, what happens to the light? It pitches backwards. So that is nothing but the reflection which is taking place. It hits the object, it gets back to the same position. So that is all about the reflection. What are we studying about? Waves also. So here, when mechanical wave reaches the rigid boundary or a body, it gets reflected. So there are two types of reflection of waves, whatever we study, and those are said to be echo and reverberation. So in terms of echo and reverberation, what is meant by echo? What is the difference between this echo as well as reverberation? So both are one and the same, but echo is the one you can hear it after a while after the audio is produced. Reverberation is nothing but the persistence of sound even after the source is stopped. Okay, so that is all about reverberation. For example, you can see it in a hill stations. Whenever you give an audio, what happens? You get your audio even after you stop screaming. Later onwards, that is after certain time interval, you receive the audio backwards. That is, the audio is reflected. The longitudinal waves are reflected back to you. So that is all the difference between this echo as well as reverberation. So echo, the sound heard after the reflection at a distant rigid boundaries such as walls, buildings or cliffs, hill stations. So reverberation is nothing but retaining of the sound even after the source is stopped. So that's all about echo reverberation. Next, let us move to the standing wave. So what is meant by a standing wave? A standing wave is nothing but a stationary wave which is at rest. So can you say that the wave will be at rest? No, the wave, we can never find the wave at rest, but we can visualize it. How do you visualize it? That is, there is a movement of wave, that is, there are superposition of two waves which is moving in an opposite direction. So when the two waves which is moving in an opposite direction superimpose on each other, what happens to the wave? The wave seems to be, it is stationary. So here, that is all about your standing wave. It is already given, that is, when two progressive waves, the one which progresses, that the one which moves forward. So two progressive wave of the same length and having same amplitude, it travels with certain velocity which is said to be the same velocity for both the waves. When it travels through same velocity in opposite direction, and when it superpose on each other, the resultant wave pattern appears to be a steady pattern or a stationary one. So here you can observe there are two waves which are superimposing on each other, wherein here there is a slight difference in the amplitude, but in case of the stationary wave, there is the same amplitude, same velocity as well as the same, it has got the same length. So when that is the case, when it superimposes, the resultant wave is said to be a steady one or a stationary one. So here, nodes, it consists of certain terms. Those terms are nodes, antinodes and loop. So what is said to be a node? So here, position at which the amplitude of vibration of particle is said to be 0. That is, there is a formation of nodes and antinodes in this manner. So when this is the case, nodes means the place where it joins and antinode means the place where it is open. This part is said to be antinode and here it is said to be node. So here in this case, it is nothing but the amplitude of vibration. So vibration, that is the height of this wave, both also merges over here. So the height coincides, that is the amplitude of the wave is said to be 0. In case of antinode, the position at which the amplitude of vibration is said to be maximum. Here its amplitude A is said to be maximum. The amplitude of the vibration of the particles. The particles always vibrate. So vibration of the particle, that is the amplitude of vibration is said to be maximum. Next is loop. That is the waveform between two consecutive nodes are called as segment or a loop. So here if there is a presence of node, between two consecutive nodes, there is a presence of certain gap, and that gap is said to be segment or a loop. So I hope you're clear with the nodes, antinodes as well as segment. Nodes are the one where it is joint, antinode the space where you have got, that is the open one, open space, and segment is nothing but the gap between two successive, that is two consecutive nodes. So now let us move to the characteristics of the standing wave. You know the difference between progressive wave and standing wave. Progressive wave are the wave which keeps on moving, correct? So the standing wave is the one which doesn't move. It represents the steady state or the stationary state. If in progressive wave the energy is transferred from one particle to the other particle, in case of the standing wave, here the energy is not transferred. So here the waveform doesn't advance through a medium. So I told you it doesn't advance. It is in a steady manner or a stationary wave. Next is the flow of energy across any section of the medium. There is no flow of energy. Okay, and the third one is the amplitude of vibration from point to point. It gradually increases from node to antinode. At node the amplitude is less, at antinode the amplitude is more. The amplitude of vibration will be maximum. So which is the particles which is lying between two nodes moves in the same direction. If the particles are present between two nodes, that is in the segment or a loop, the particles move in the same direction. That's all about the characteristic of a standing wave. So after this we have got the stationary wave at the air column. So here we are studying regarding the waves, how it reacts in the air columns. For example, you can consider the air column as a flute instrument. So here we are talking about the stationary waves. So here a column of air is enclosed in a pipe. Okay, so you can see a pipe over here, a column of air is enclosed in a pipe. So after which there is a presence of water. So whenever there is a presence of air and whenever you pass any sound through that medium, what happens? That is the action which is taking place within this air column, that is air enclosed column, we are checking now. That is, if this is your tuning fork, you just produced a vibration to this tuning fork and place it on the column. What happens to the sound produced in the air? It travels through the column, that is with the help of a medium. So when that is the case, let us check how the sound wave is produced within the air-filled column. Here we are considering two types of pipes in order to study the nature of sound waves within the air-filled column, and we consider two types of pipes, that is closed pipe as well as open pipe. Before that, let us understand certain terms to know our fundamental mode. So the mode of vibration at lowest frequency is said to be a fundamental mode, and corresponding frequency will be fundamental frequency. So what is meant by overtones? Overtones are nothing but it's a mode of vibration which produces higher frequency. It is producing notes of higher frequency. So that is all about your overtones. And harmonics are nothing but if the frequency of the overtones are said to be integral multiples. This is very important. That is the harmonics. When can you say it is a harmonic one? That is if the frequency of the overtones which we receive are integral multiples of the fundamental frequency, then we can say it as harmonics. So that is all about the terms which you have to know before getting into the modes of vibration in open as well as closed pipe. So now let us see the mode of vibration in terms of a closed pipe. That is one end of the pipe is said to be closed over here. You can see how the wave is produced by this image. So here there is a presence of length, that is this is the length of the air columns. This pipe or a tube is closed at one end which is filled with the air molecules. That is a wave, for it to travel it needs a medium, okay, and that medium is nothing but the air medium, and the particles are the one which is responsible for the production of sound, that is the audio, okay. So here for a longitudinal wave, here we have considered a air column which is a closed pipe at one end, and let us name nodes as well as antinodes. So we have got segment, and this segment is half segment. So here we have got which segment? It is just half segment, wherein this is antinode AN and this part is said to be node. Again we have got two nodes over here. So one node and two node. This is said to be antinode and this is also said to be antinode. So how many segments are there? Here there are, this is one segment or it is a loop, and here it is half. So it is 1.5. Next, let us go to the third column. So here we have got node and node and node. So there are three nodes. So this is the antinode, that is the amplitude of vibration is said to be maximum at this part. That is why it is called as antinode, where there is no formation of any sort of node. That is merging of two waves. So when this is a case, here you have got, this is one segment, this is the second segment, that is two segments. Let me consider it as one, this as one, this as one, and this as half. So here you have got 2.5 segments. So what are the segments over here? This has got half is a segment, and here you have got 1.5 as a segment, and here you have got 2.5 as the segment. Now let us see to the ratios of the frequencies, that is overtone frequency, how it is going. So here we have, let us consider the first term. Since we have L is equal to the number of segments, what is the segment? It is just half. Half segment into the distance between two successive antinodes and nodes. Distance between two nodes is said to be lambda by 2. Distance between two nodes and two antinodes is nothing but lambda by 2. It is said to be distance between two successive nodes and antinodes. When we have this case, let us assume 1 by 2 into lambda 1 by 2, because I am considering the first column. That is why I am considering the wavelength of the first one, lambda 1, which is given as lambda 1 divided by 4. And we have lambda 1 is said to be 4 into L. I can consider it as 4 into L, which can be written in terms of frequency. So frequency nu is equal to V divided by lambda. It is V divided by lambda. So when that is the case, we have got V by lambda equation 1, and that lambda value is nothing but 4L. So I can write frequency as V divided by, since it is lambda 1, it is 4L, said to be equation 2. So we have frequency nu is equal to V divided by 4L. That is, frequency is equal to ratio of velocity as well as the length. 4 times the length. So that is all about only this first figure. Figure 1. Now let us check into the figure 2. For figure 2, let us consider, for figure 2, we have length L is equal to how many nodes, that is how many segments? It is 1.5. 1.5 segments. So it is like half plus 1.5, you will get it as 3 by 2. 3 by 2 will be the segments. So which you have, that is one segment plus half is 3 by 2, and it is given as lambda 2 divided by 2 because it is the distance between two successive nodes and antinodes. So you have got this equation as 3 lambda by 2 divided by 4, so that your lambda 2 becomes 4L divided by 3. So this will be the equation for lambda 2. When you apply it to frequency, you have got nu is equal to V by lambda, which is said to be V divided by 4L. 3 goes to denominator, which can be taken to numerator. So you have 3V divided by 4L. This is said to be equation 3. So it is like you have got the frequency for one and the frequency for the other one, that is said to be frequency 2 for the second figure. For the third figure, you will have like for figure 3, you have got L is equal to how many segments? It is 1 plus 2, 2 and half. So it is 1 plus 1 plus 1 by 2. You will get it as 5 by 2. So it is 5 by 2 by taking 1 plus 1, that is 1 plus 1 plus half. You will get it as 5 by 2 because of the LCM which you are taking, that is LCM conditions. So segment will be lambda 3 divided by 2. So it becomes lambda 3 is equal to 5 by 4. It becomes 4L divided by 5. So when it is like 4L divided by 5, because this goes along with this and 5 comes down and lambda 3 is the equation. What is your frequency? That is nu 3 is equal to V divided by lambda, which gives you V divided by 4L will be in the denominator, 5 goes up. So you get 5V divided by 4L, that is the third frequency of the third figure. So having all this, what happens to 1, 2 and 3 figures, the nodes and antinodes which is formed in 1, 2 and 3 figures, it gains, that is the frequency nu1, nu2 and nu3, and the equation is like, so for these columns the equation comes out to be nu1 is to nu2 is to nu3. So these three are the ratios. Ratios of 3 is given by 1 is to 3 is to 5. So these are in integral multiples. Okay. So at this position, the frequency was known as fundamental frequency because it was a lowest frequency, and at the rest of the two, it is said to be second harmonic, as well as the lastly, the 5, that is the number with whatever the value you have got for the frequency 3, third frequency, is said to be third harmonic. So having these concepts, you can conclude that the ratio of the frequency which is present over here are in integral multiples. So if that is in integral multiples, as we had studied in terms to know, it is nothing but the overtones. So we can conclude that only the odd harmonics are present in the vibration within the air column under closed pipe. So now let us move to the modes of vibration of air column in a open pipe. That means in a previous case you had studied the closed pipe, but in this case we study regarding the open pipe. The pipe is open at 2 ends. So what happens to the wave which is associated with certain pipes? It is like here you have got your antinodes, here you have got your node, and here it is again back to antinode, and this is said to be the length of the air column. Again you have got your antinode, node, antinode, node and antinode. In this case again you have got your antinode, node, antinode, this part is node and antinode, and this is node and antinode. So this is how you have got. So when you conclude this, when you consider this, you will have your length L is equal to, for the first one, your length L will be, you have got how many segments? It is same as that of the previous one, whatever you have done. Have got half plus half. When it is half plus half, it is 1 into segments and lambda by 2. So your equation becomes lambda divided by 2, and it is said to be lambda 1. Let me consider for the first figure. So it is lambda 1 is equal to 2L. That will be your the wavelength, and the frequency nu is given by V divided by lambda 1, which can be given as V, that is V divided by 2L. So this will be your equation for the first one, that is for the first frequency in the air column which is open. Next let us go to the second one. For the second one, what will be your L is equal to, you have got 1 half plus half. So you have got on the total 1 and half plus half is 1. So 1 plus 1 together it makes 2. 2 into lambda 1 divided by 2. So 2 cancels and lambda 1 remains, wherein you will take the frequency nu as V divided by lambda 1 is nothing but 2L divided by 2. So 2V and 2L remains. So this will be your second frequency for the second frequency nu 2. Next, Here in this case, lambda also will be 2 in nature. In third equation, you have got one segment. This is one segment. This is two segment. That is the second segment, and half. Half plus half, you have got 3. One segment, two segment, and 3 segments. You have got 3 into lambda 3 divided by 2. So it becomes like you have got your lambda 3 as 2L by 3. When you opted for frequency nu 3, you will have V divided by lambda 3, which is given as V divided by lambda 3 is nothing but 2L divided by 3, and 3 goes up, it becomes 3V divided by 2L. So you have got V by 2L, 2L by 3, which is given as 3V 2L. So you have got 1 and 2 as well as 3, 2V by 2L. Having all these things, you have got ratio of frequency nu1, nu2 and nu3 as, which is given as 1:2, that is 1 by 2 V divided by 2L, that is cancels. So what remains here in the sense 1, and here 2 remains, here 3 remains. So 1:2, 2:3. So what are the ratio of frequency in case of the modes of vibration in open pipe? It is 1:2, 2:3, which are said to be, that is these harmonics are said to be natural numbers. So once again, it is named as fundamental frequency because it is having a lowest frequency, then it is second harmonic and third harmonic. So here it is the harmonics. Harmonics are said to be in natural numbers, that is 1:2:3, which is in a continuous numbers. That is all about your motion of vibration in case of air columns in a open pipe. So you have studied the modes of vibration in open pipe as well as closed pipe for now. Now let us move to the beats. So what is said to be a beats? Beats is a sound wave, whatever you can hear. How is that you can hear? It is like mixing up of too many instruments. You listen to music. So what happens in case of music? There are too many instruments which gives its own unique sound. So it has got its own sound waves with certain frequency, certain amplitude, which moves with certain velocity. So here those different music instruments are merged together to give a one beautiful tone. Okay, so that is all about your beats, that is tuning up of a resultant wave once you get each and every waves from each and every surroundings. So it is like waxing and waning. It is said to be the word waxing and waning of the intensity of sound due to superposition of two sound waves. So here you have got two sound waves. Let me consider this as first sound wave and let me consider this as a second sound wave. So there are two sound waves which are added up together, the first sound wave plus the second sound wave, which will give you a resultant wave. So there is waxing and waning, that is the pitches are high as well as low. There is periodic rise as well as fall in the wave which is produced, that is in the resultant wave. At this position you can say that the audio is very loud, and at this position, that is at the notes formation, you can find that the audio is feeble to listen. So that is all about your beats. Now let us move to the Doppler effect. So what is this Doppler effect? It is a very easy concept and we observe it in our daily life. That is nothing but the apparent change in pitch or the frequency of the sound which is observed, that is heard by the observer in relative with motion between the source as well as the observer. That is all about this diagram you can see over here. That is at stationary point, waves are said to be in a medium state. So when there is an observer who is present and the ambulance is moving towards the observer, what happens to the sound which is heard by the ambulance? We hear it louder and louder, because of which we can get to know that an object or a particle is arriving near. And when it is moving away, that is when it is moving away from the observer, what happens to the sound waves? It becomes feeble. That is, we get to know by listening to the sound itself, we get to know that is the object is moving away from the observer. So that effect is known as Doppler effect. It always depends upon the motion of observer as well as the source. That's all about the concept of Doppler effect. In today's class, we have studied regarding the Newton's formula for the speed of sound in air, and we have studied the correction with respect to the same formula, that is Newton's formula. We studied what is meant by superposition of waves, what is meant by standing waves, its characteristics, and how the standing waves react in case of a air-filled column of pipe that can be open pipe or else a closed pipe. And we studied regarding beads, that is waxing and waning of the superposed waves, which are known as beads, is also studied. And then we have studied regarding the Doppler effect. So here ends our chapter 15, that is wave. And that's all for today. Have a good day. Thank you.